Hello everyone. So in the last class we discussed about the light reflection and the reflection in plane mirrors. So today we will be continuing our discussion to spherical mirrors. So these type of mirrors are those mirrors which are basically not having a flat surface. So what are these type of mirrors? Actually these are nothing but a part of a hollow sphere. For example, if I draw a sphere like this, suppose this is a hollow sphere. Suppose this is a hollow sphere. First of all, let us write this definition that uh, these are these are the mirrors. These are the mirrors whose reflecting surface is part of a hollow sphere. Suppose this is a hollow sphere. So what I am telling you is that this mirror can be a part of this. Suppose say from here to here, this one, this part. Let us say this one, this portion over here. This will be your you can say type of spherical mirrors, and the reflecting surface, as I told you, it can be on either side. It can be on this side also, or it can be on this side also. If the reflecting surface is inside this hollow sphere, okay, that means always I mark these dashed lines which represents that this is a non-reflecting surface. So this is your reflecting surface here. So this is your reflecting surface. So if this is the case, if reflecting surface is, you can say it is inside of this hollow sphere, then this type of mirror is called as concave mirrors. This is called concave mirror. Okay. Similarly, a case can be there such that suppose again you see that this is a hollow sphere, and I am telling that yes, okay, fine, this is the part of the hollow sphere, and now I'm telling that the reflecting surface is on this side. Now this is your reflecting surface. This is your reflecting surface. Now you can see that this reflecting surface is outside. It is outside of the sphere. So this type of mirror is called as convex mirror. This is called as convex mirror. Okay, this hollow sphere is made of glass. Okay, so this is the part. So basically we are having two types of spherical mirrors. One spherical mirror is concave mirror, another one is convex mirror. So these are the two type of mirrors. So concave in the sense you can understand like this with the help of a spoon. Okay, suppose I consider a spoon like this. This is a spoon. The spoon is like this, and then this is your handle to hold the spoon. So this is the spoon. Uh, Speaking of a spoon, both sides are shiny, both are reflecting surfaces. So if you are considering the reflecting surface on this side, then you can see this kind of structure is formed like a cave type of. Okay, so this you can learn by this analogy that concave means that this kind of a cave, that means a inside bulging type of a shape is a concave shape, and when the reflecting surface is on this side, then this is called as a concave mirror. Similarly, if you consider the reflecting surface on this side, if you consider on this side reflecting surface, then it will be a convex mirror. So this is the meaning. Okay, so this is a general types of spherical mirrors. So these are the two type of spherical mirrors, which is concave mirror and convex mirror. Now since these are part of a sphere, so we will have some of the landmarks for these mirrors, some specific points for these mirror where analysis is made with respect to these reference points. So let us draw this diagram separately and understand those terminologies which are involved in the spherical mirrors. Now I am telling this is your sphere, okay, and let us consider both the convex and concave on this same part only, okay. So however, the for a particular sphere the reflecting surface can be either on the inside or either on the outside, but for analysis let us consider that we are considering, let us say this is a mirror, okay, this is a mirror, and this is this type of mirror is this, let us say it is a convex mirror, concave mirror, sorry, okay, this is a concave mirror, because why, because reflecting surface is inside, right, and let us see that the center of this sphere is this one, okay. So this is the center of the sphere, let us say. So whatever for of which sphere this concave mirror is made, the center of this sphere is called as the center of curvature. So this is called as the center of curvature, okay. So this is the center of curvature is nothing but it is represented by, center of curvature is represented by, let us say we are marking it by C, okay, this is C. And through this C, what you can do is, suppose this is your mirror, through this C you can draw a straight line like this, okay. Through C you can draw the straight line like this, let us mark this straight line. So you can see that this is a straight line. We divide basically the center of curvature with this divides this sphere into two parts, passing through the center of curvature and cutting this mirror at a particular point, okay. So wherever, so this is an axis which passes through the center of curvature. So this particular axis we call it as principal axis. It varies from minus infinity to infinity, that is means it is a line, okay, and that axis is called as, it is an axis, it is called as principal axis, which is passing through the center of curvature, and it cuts the mirror at a point. It cuts the mirror at this point, you can see we mark it as P, and this point is actually on the middle of this mirror, and this is called as pole of mirror. So this is represented by P, center of curvature, by C. Obviously you can see that now this distance from pole to center of curvature of this mirror, this is called as, this particular distance is called as radius of curvature. Obviously because through center it is passing to a point on a circle, you can say, if you consider it in 2D space. So this is radius of curvature. This is radius of curvature. So radius of curvature is nothing but represented by R. Okay, like this. Similarly, you can consider it for a convex mirror also. These terminologies, these things remain same. Okay. Now we will learn about what is the aperture of a mirror. So aperture of mirror is not that important in our analysis, but you must know what is the aperture of mirror. So aperture is nothing but this point, this type, this reflecting part. The length of this reflecting surface, this part is called as aperture. So we consider that while we are considering the concave mirrors and the convex mirror, which we assume that the aperture is very very small. That means I am drawing this concave mirror such a large part over this sphere, but in practicality this will be much smaller than this. That means that aperture will be very small. You can understand this aperture by on this figure as arc. Okay, basically if I consider this as, if I am seeing it in 2D, I can see this as a circle. However, this is a sphere. I can see it as a circle and an arc on this circle. I can see it. I am marking it as concave mirror. So you can understand by this way also that this arc is very small. That means this aperture is very small. Okay. So this aperture is very small. Okay. So if the aperture is very small, then in that case, the midpoint between pole and the center of curvature, we mark it as, suppose, let us use a different color. Suppose this is the middle point. This is the middle point, and then this distance and this distance. Obviously, then if this aperture is very small, then only that case we can see that the distance between this and this and this and this will be equal, and we mark this point by F, and this is called as the focus. We call this point as focus of mirror. So this is focus of mirror, and the distance from either side, that is from P to F or F to C, either is called as focal length. This is nothing but focal length. So it is denoted by small f. So you can see that the radius of curvature and this focal length will be having a relation. By here you can see that R, that is the radius of curvature, this complete distance is nothing but 2f. So this is a relation which you need to remember, and this is occurring only when this aperture, that means this mirror, is a very small part of this hollow sphere. Then only that radius of curvature is equal to twice the focal length. So this is all about the terminologies. You must know what is center of curvature, focal length, this is the focus point, this is the pole. Pole is nothing but the center of a mirror, basically, through which this principal axis is passing, and it is connecting the center of curvature, focus point and pole. See, these all 3 points, these 3 points are lying in the principal axis. So whenever we will be drawing the ray diagrams for these mirror, concave mirror, convex mirror, we won't be drawing this whole sphere. We will just be drawing the mirror and marking this principal axis and the points over that, and then we'll be drawing the ray diagrams and making analysis on these concave and convex mirror. And this relation, you must understand that the twice the focal length is nothing but the radius of curvature. Pretty clear this must be. Now uh, let us go deeper into the how these convex and concave mirror will be behaving to light. So I told you that now I will be drawing the mirrors like that. So suppose this is your concave mirror. Obviously, if this is the middle point, I will be marking the principal axis like this. Okay, suppose this is the principal axis and this is nothing but a pole. This may be somewhere half and this will be equal distance, so this will be C. So like this I will be drawing. So what will happen? Now rays of light, obviously this is the reflecting side. This is the reflecting side of the mirror. This is the reflecting side of the mirror. So on the reflecting side of mirror, we will be making the light incident. Okay. So what will happen? There is another definition of focus point. And in case of concave lens, concave mirror, sorry, we will be seeing the concave mirror. So when rays parallel to this principal axis, suppose this is your incident ray, there are incident rays coming parallel. This is your incident ray, this is also your incident ray. So these incident rays are coming parallel to this is your principal axis, right? So these incident rays are coming parallel to the principal axis. So what happens in concave mirrors, when these rays are parallel to the principal axis, they will follow the laws of reflection here. Obviously this is your point of incidence, this is your point of incidence, these red points. Okay, so here you will be following the laws of reflection, and this is, I told you that again you will draw the normal. So this is your surface, normal will be somewhat like this. Okay, somewhere like this will be the normal. Okay, So what will happen? This angle of incidence equal to angle of reflection. So like that, the reflected rays will be passing through the focus. Here also it will be obeying the laws of reflection. So these are your reflected rays, the red ones. So when the rays are parallel to the principal axis, they are passing through this point, which is called as the focus point. So through this point, what happens? We can define focus point as for the concave mirror as focus point. Okay, the point, the point, the point on the principal axis. The point I will write PH. Okay, the point on the principal axis on which the reflected rays intersect. Reflected rays intersect when incident rays are parallel to principal axis. Okay, so whenever these rays are parallel to this principal axis, the point where they will be meeting is called as the focus point. Now one more thing you can observe, that this is your concave mirror. This is your concave mirror. Okay, and what is happening? This was your principal axis. Okay, and what we observed, that what it is doing, if you consider this ray of light, it is focusing this ray of light on a particular point like this. Sorry, through the focus it will be passing, so like this. Okay, this, so like this it will be passing through the focus. So what is it is doing, that the rays when are parallel to this principal axis, they tend to converge at a point, they tend to meet at a point, they are meeting at a point. That means this type of mirror is converging this beam of light. Okay, so this you can observe. So this is about concave mirror focus point. Similarly, if I consider now the convex mirror. Okay, so convex mirror, as I told, that it will be having the reflective surface on the other side, and this non-reflective surface on this side, and the reflective surface is on the outer side. Okay, now similarly I will draw the diagrams for this also. So this is like the principal axis for this. Okay, and this is obviously the pole, right? And I can consider this focus point. I will be marking focus point here and somewhere C here. Okay, and equal to this. Now, what we will be observing is that, now suppose the parallel rays are made. Okay, these incident rays are made parallel to the. This is an incident ray made parallel to this principal axis. Now for reflection, we will be seeing the laws of reflection here. So at this point, this is the point of incidence. So from this point we will be marking the normal, and then this angle of incidence will be equal to the angle of reflection. So like this, what will happen? The ray will be forming. So this is your reflected ray. Now observe that incident ray, when made parallel to the principal axis, they diverge away. They diverged. The reflected rays diverged away. So you can see this convex mirror. This convex mirror, you can see that it is diverging these incident rays. Now, if you are observing from this side, obviously from the reflecting side, observer will be there. Suppose you will always be observing on the reflecting side of the mirror. So this is your eye. So to your eye, if these rays, suppose here you are observing. Okay, so when these rays reach your eye, to your eye it will feel that these rays are coming from this. If I drag draw this will exactly, because these are not very accurate in terms of uh, measurement, so it is a bit rough diagram, but you can understand that if I back trace these diagrams, these rays, this appears to come from this point. So the reflected rays, you can see that reflected rays appear appear to come from F. So that is why when the incident rays in a convex mirror are parallel to this principal axis, and when the reflected rays are appear to coming from a point on the principal axis, that point is known as focus point. Since we are saying that they appear to come from focus point, that's why we call the focus point in a convex mirror, the focus point in a convex mirror, okay, in convex mirror we call this focus point is as virtual focus, because these rays are not actually there, but they appear to come from this focus point, kind of a virtual image kind of discussion. Okay, so these rays of light come from this focus point, okay, which is actually behind the mirror. So whatever the reflecting side we consider as front of mirror, okay, front of mirror, and non-reflecting sizes we called it as back of mirror. Okay, so this is your non-reflecting side here, this side, this portion over there. So that is why we are calling that this is the back of the mirror. So this focus point is lying on the back side of the mirror in case of a convex mirror. Now there are certain laws by which ray diagrams are to be made. See what will be happening in case of a plane mirror. Anywhere you put the object, same nature of image was observed. Whether you are standing 100 meter away, whether you are standing 50 meter away from a plane mirror, always a virtual, literally inverted, erect image equidistance from the mirror will be formed by the plane mirror. But in case of spherical mirrors, what will be happening is that depending on the distance of the object from the mirror, different nature of images will be observed. So to analyze this, we need to consider ray diagrams, and for drawing ray diagrams there are certain rules. So rules for drawing ray diagrams. Okay, in case of these mirrors, we will be seeing these rules. So we will be discussing uh, these laws. Okay, so first one we will discuss. Let us consider this concave mirror, and this is nothing but the first point discussion. We have already seen what the focus point. This is same as it is, that is whenever the incident rays are falling on this mirror parallel to the principal axis, then what will happen? They will pass through a point which is called the focus. Okay, this is the first law, that whenever the incident ray is made parallel to this principal axis, then it will pass through the focus. If it is a convex mirror, what will be happening? If it is a convex mirror, then what will be happening? If the rays are parallel to this principal axis, then this will be actually uh, reflecting back away from this mirror, but appear to come from this focus point. So this is your first law. Now the second one is that it is just the, suppose this is your concave mirror, and I am marking again this principal axis. Okay, so this is, let me draw accurately. So this is your, let us say this is your principal axis, this is pole, obviously this is F, and obviously equal distance to this F and P there will be, see, consider if we consider this aperture to be very small. And now this law states that, second rule you need to remember, that whenever incident ray is passing through this center of curvature like this, okay, whenever the incident ray is passing through the center of curvature, what will happen? The reflected ray will be bounced back to the same path. Okay, so incident ray, if it passes through the center of curvature and hits the mirror, then it will pass through the center of then it will pass back to the center of curvature. That means exactly reflected ray will follow the path of the incident ray. It will be retraced back. Okay, so this is the case. Okay, so similarly, in if it is a convex mirror, what will be happening? If this is your principal axis, in this case, this is your F, this is your C, say. So if a ray is such that if it is incident in line with the with this, okay. So what will be happening if this is the incident ray and such that it appears that it will be passing through the center of curvature? What will be happening? You will be observing that the reflected ray is also coming from the center of curvature. Okay, so these are the first two rules which you need to remember. Now let us look at the last one, that is the third rule for drawing the ray diagrams. Okay. So third one is this. Suppose this is your concave mirror, right? And this is your principal axis. Obviously, this is your F, this is P obviously, and this is C. Now I am telling that if incident ray is striking the pole, so what will happen? At this point, this is acting as the normal, because at every point it will, in all these rules, we are always obeying the laws of reflection. Remember that. Because suppose this case I was telling that incident ray is made, if it is passing through center of curvature, then it will follow back, the reflected ray will follow back the same path. Why it is happening? Because this will be the normal of this surface only. So if incident ray, suppose this is the surface and this is your normal, okay, 90 degree. So if incident ray is on the normal itself, then angle of incidence is what? Angle of incidence is what? It is 0. Angle of incidence is 0. If this is the incident ray which is uh, tracing or which is overlapping with the normal, then incident angle is 0, because angle of incidence is what? It is the angle between the incident ray and the normal, but incident ray and normal are overlapping each other, so that means angle of incidence is 0. So what will be angle of reflection also? It will be also 0. That is why the reflected ray is returning to the same path, because this is the normal itself. Okay, that is why this is happening. Now if I consider the pole, so at pole, this will be completely 90 degree. This will be your surface at pole. So this will be normal. So what will be happening? The reflected ray will be such that these two angles will be equal. This is nothing but the meaning. This is the your third set of rule for drawing ray diagrams for the spherical mirrors. Now let us consider this one in case of a convex mirror also. Obviously I will be drawing the, this is your pole, this is your focus, this is your center of curvature. And now according to this, if this is the case of an incident ray, again this will be acting as your normal, right? This will be your surface at this point, so this will be your normal. This principal axis is itself becoming the normal, so this angle will be equal to this angle, so it will follow this path, right? So this reflected ray will be in this path. This is the angle of reflection. So these are all the rules for drawing the ray diagrams in case of spherical mirrors. These 3 points we must know. So we can now draw ray diagrams for an object placed anywhere on the principal axis of these mirrors. So let us now consider the first mirror, that is nothing but a concave mirror. Now we will be ray diagrams we will be drawing for concave mirror. Okay. So for different position of object, we will be considering the where the image will be formed. Okay. So let us see the first case when object is at infinity. That means very far away from the mirror. Okay. So we will be seeing this case. So I am drawing this ray diagram also. Suppose this is your concave mirror and the middle of this is pole, and now this is your principal axis. Let me draw it accurately. Yeah. So somewhat like this we will be having. This is your focal point, this is your center of curvature. Now we are telling that the object is at infinity. So if it is infinity, that means from far away the rays will be coming. From far away the rays will be coming. So like this the rays will be coming. Like this will be coming. Say they are coming parallel to the principal axis. So where they will be meeting? They will be the reflected ray will be passing through the focus point. Just now we discussed the rule. Okay, this is point of incidence, so it will be passing through the focus. So if object is placed at infinity, so from that object these rays will be coming. Let us consider these two rays and these will be passing through the focus. Now the formation of a image will be such that wherever these reflected rays meet, they will be forming an image. So you can see these two reflected rays are meeting at this point. So this is nothing but your image. Okay, so this is nothing but your image. So if the object is placed at infinity, that is very far away from this concave mirror, what will be happening? These rays will be coming like this and they will be meeting at a point. So what the size of the image should be? These reflected rays are meeting at a very small range of distance. These rays are meeting at a very small range of distance, that is they are meeting at a focus point. So you can see that what will be the size of the image, it will be diminished. So we will be commenting on the nature and size of image. Nature, position and size, right? So first of all, if I talk about nature, are the reflected rays actually meeting at a point? Yes, they are actually meeting. We are not tracing any ray of light. They do not come to up there. They are not appearing to meet at a point. They are actually meeting at a point. So that means the nature of image is real image. So real image is formed. Where is the position? You can say that the reflected rays are meeting at the focus. The position is at focus point at F. And what about the size of the object? So this object is very far away. That means let us say suppose some height of the object will be like this. So we obviously represent object like this. Okay, like this arrow we will be representing, where this height of this arrow will be representing the height of the object. Okay, so somewhere infinity this object is placed. So obviously it is having some height, but now it is getting converted to a point sized range. Okay, so we can say that the image is highly diminished. Image is highly diminished. So this is the first case. Okay, where the object is placed at infinity. Now let us bring the object a little bit closer, and now let us place the object at somewhat nearer to the infinity case. That is, let us now consider the object to be placed at beyond C. Suppose this is your pole point, obviously focus, center of curvature. Now the object is pretty much visible, and I am telling that the object is placed at this point. Okay, so object is placed at this point, and this is your object AB. So I am taking the second case when object placed at beyond C. That means not at C, somewhere far away from C, but not that as in the case of infinity. So now we will consider the ray diagrams. So first of all, for an image to form, we will be considering at least so many rays will be emitting from this. Okay, and we need to consider that only two rays at least. So if the two rays we are considering and then the reflected rays are meeting at a point, that point we will consider the image point. So this is the whole concept. So suppose one ray I am considering, so this will be parallel to the principal axis. Obviously it will be passing through the focus, right? Let us extend this. This is the reflected ray. Okay, this is your incident ray, reflected ray. Another I can draw is that one is like this. Suppose if the rays incident is on the center of curvature, right? If it is incident on the center of curvature, so according to the rules of reflection, this will the reflect incident ray after striking this point, it will be reflected back in the same direction. So this is the reflected ray. This is your reflected ray. This is also a reflected ray. It is meeting at this point. So this point we emitted the rays of light, two rays of light from this top of this object. So this will be obviously top of this object. Okay. So it will be object will be like this. This is the top. Right. So you can observe that now we can consider the nature, image, nature, the position and size of the image. So what is the nature? Obviously, really they are meeting the reflected rays, so real image is formed. What is the position? We can see that it is between C and F, between center of curvature and focus point when the object is placed beyond C. And what is the size? Obviously, this was this much large, so size is being reduced. We can say that the image is diminished. The image is diminished. Right. Similarly, we can now take the further cases, right? So now let us consider the case of when the object is brought furthermore near to this principal axis. The object is now at C. Let us consider the object is at now C. Okay. Let us now consider the object is at C. So this is your C point. This was your F, right? So object is at C. That means at the center of curvature the object is placed now. Again we will draw the incident ray. I am considering this parallel to this principal axis. So it will be passing through the focus point, the reflected ray. And another I can consider the incident ray as passing through the focus. This inverse is also true. Okay, if this incident ray is passing through this focus point, then the reflected ray will be parallel to this principal axis. That is also the point. So there is somewhere in this diagram, maybe somewhere here the focus point is there, right? Like this, and somewhere let me consider this. This is not actually equidistant, so that is why it is getting some problem. Right? Somewhere here the focus point. Alright, so let us say here will be your focus point. And now if I make this very parallel to this, It will be passing through the focus, right? And if the incident ray is passing through this focus point, it will be actually meeting at a, it will actually cut at this point, which is center of curvature. This is the top of the image now, because this was your incident ray, this is your reflected ray, and this was your incident ray, and this is now reflected ray. So both these reflected ray, this one and this one, are meeting at this point. So this will be top of the image. So I can say that actually they are meeting, so the real image will be formed, the image formed will be real. The position of image is obviously at C. The position of image is at C only, right? And what is the size of image? It is same size. Now one more thing I can see, that the image formed is upside down. You can see the image formed is upside down. So when the image is formed upside down, I call it as inverted image. I can add this point also, that it is an inverted image also, because the image is upside down. Also in the previous case, when I saw the object was at F also, although the object image was highly diminished, the image was inverted. Remember that whenever this real image is formed, it is inverted image only, right? So that is why whenever this real image is formed, you can consider that the image is inverted as well. Also, when we saw that when object was placed beyond C in previous case, then also the object was, the image was diminished, but it was also inverted and real. So whenever this real image is formed, the image is inverted also. Okay, and the size is this time same. So this is how you draw the ray diagrams. Now let us consider the next condition. Uh, okay, now we will be considering mm, the fourth one, where the object is at, the object between, now this one is object between C and F. Okay, when the object is between C and F, I will mark this as the pole. Okay, because I am drawing rough diagrams, so some points are not rays are not becoming as I want, but yeah, fine. That is, this is F, and this is your, let us say this is your C. Now I am telling that the object is placed between C and F. That means somewhere here the object is placed. Again, I will draw the incident ray. Take the top of this object. I will draw the incident ray parallel to this principal axis. It will pass through this focus point, right? Similarly, now I will pass the incident ray through the focus point, right? And then I will draw this parallel. So somewhere here the object is formed, and now you can see that this is the top of the reflected rays are meeting here. So this is where the object is formed, and you can see the size has increased. Okay, the image size has increased. I am marking this object by AB. So A dash B dash is the your image size. Okay, now I will comment on the nature, position and size, right? So what is the nature? Obviously it is real image, and you can see that it is, image is upside down, so it is inverted. Obviously if it is real, it will be inverted image. Now the position of image, where it is, when the object is placed between C and F, you can observe the image is formed beyond C. And what is the size of the image? The size of the image is what? Enlarged, because now the object, you can see that the size has somewhat become enlarged. So till C, you are seeing that when you place the object at infinity, the image size was highly diminished. When you took the object to beyond C, some size was somewhat increased, but still it was diminished. When you took it at C, the size is the same. And as you move further from C, you take the object further near to the pole, near to the sea, the image size is increasing. So what is happening? The distance of the object is inversely proportional to size of the image. The distance of object is inversely proportional to the size. So if the distance is farther away from the pole, distance of object I am considering is from pole only, that is P. So distance of object is far away from the mirror. The size of the image is what? Small. As you bring the object closer to the mirror, the size of the image is increasing. You can see very much clearly. Now between C and F, the size is now become enlarged. First of all, it was highly diminished, then of the same size, now it is becoming enlarged. So this is what? C and F. So now let us see the case when the object is placed at F. So now I will be drawing this concave mirror. So yes, so while watching you will also develop a habit of how you can see, and you can again when you are seeing that how the ray diagrams are being made, then you can easily draw them. So F and C, and this is pole, right? I am telling when the object is at F, that means this is the position of the object. So let us draw the incident ray. So I am taking this top of the object. This is your object AB. Obviously, if I take this parallel to this principal axis, the reflected ray will be passing through the focus. Okay, that is fine. This is your reflected ray. Again, if I am taking and incidenting this point as taking the point of incidence as this pole, so this angle and that angle particularly here will be equal. So it will be somewhat like this. This angle will be what nearly will be equal. So you can see that now these rays are coming parallel, so they won't be, it appears that they will be meeting at infinity and the image will be highly enlarged. So you can see that this will be meeting somewhere at infinity. Okay, now I am telling the nature, position and size, right? So this is what I am telling now. The nature is what? Obviously, this is the reflecting side of the mirror. So somewhere at infinity, these rays will be meeting. That we can say mathematically. That at infinity, however, at infinity will never come. So mathematically, we can say that yes, at infinity in the real world, at infinity in the real side, these rays will be meeting and forming an image. So obviously it will be at infinity. So we can say that this is a real image. Why real image? Because these reflected rays will be meeting somewhere in the reflecting side on the observer side. That is why we will say that this is okay real image. That is why it will be inverted image. So we will call it as real and inverted nature. Now the position of image is at obviously at infinity, because these rays we are saying that they are meeting at infinity, and that is why. And obviously when something is meeting at infinity, so whenever you put an reflecting screen, because if you put a screen anywhere, you will be observing this some part of object there. So that is why I'm telling that it will be real and inverted image, and it will be highly enlarged. It will be highly enlarged. That is the meaning. This is highly enlarged image, because what will be happening whenever you put a screens anywhere, let us say here or anywhere, because the image is forming at infinity. So anywhere you put the screen, you will be observing part of the object. So that is why it is a real and inverted image, because the rays will be actually meeting, forming some part of the image, some part of the object. And that is why we will say that it will be very highly enlarged. Okay, it will be highly enlarged. So you can see the contradiction, that when the object was at infinity, the image was at F and highly diminished, and now when the object is at F, the image is now at infinity and it is highly enlarged. So that is what I was telling, that as the distance decreases, as the distance of the object decreases from the pole of the mirror, the size of the image formed is getting increased. That is the meaning. Okay, so this is your fifth case. Now let us consider the last important case, in this concave mirror formation of images, because that is the case where it has a specific application. So let us take the final case, sixth case, when the object when the object when the object is at, or let us more accurately write it as, is between F and P. That is, the object is now brought further closer to the mirror. Okay, so that is the meaning. So see this ray diagram, and this case is very important. Okay, so this is pole, and obviously this part is your F, this is point is your C, and I am telling the object is now placed between F and P. This is your AB. Let us now consider the ray diagrams. Okay, incident ray is parallel to this principal axis. It will pass through the focus. Okay, let us see that. Okay, and when incident ray is incident at this pole point, just erase this part. So when this is the case, it is striking at the pole, what will happen? This angle and this angle will be equal. So it will be coming like this. This is your reflected ray, this is your reflected ray. Now what will be happening? You can see that if you are observing from this side, you can see that these reflected rays are further diverging away. So they won't be they won't be they won't be meeting in the real sense. Okay, they won't be meeting in the real sense. That means we can say that the nature of the image is what? Virtual. It will be virtual. The nature of image will be virtual. So this is the first time we will be observing that a virtual image is getting formed in case of a concave mirror. And that is the only case. Which case? When the object is between F and P. So now if I backtrace these rays, you can analyze by this. Suppose I am backtracing these rays like this. They will be meeting at this point. Obviously I took the top point and draw the incident rays from there. So this is the top point of the object, and this is the top point of the image. So this will be your image. So you can see the image is upright as it is the object. This is AB, this is A dash B. That means it is erect also. The image is virtual and erect. So virtual and erect go hand in hand, and real and inverted also go on hand in hand. That means a real image is always inverted and a virtual image is always erect. So you can see that in case of our ray diagrams. Okay, so you can see that the virtual image is getting formed and the position is now behind the mirror. So this is like your plane mirror case. In plane mirror also, what happened? The image was formed as virtual and erect, and now it is behind the mirror. Since image is forming behind the mirror, that means these reflected rays appear to come from this point. That is a case of a virtual image, right? And you can, in the ray diagram, you can see that the size is enlarged or magnified. You can use also magnified as well as the term. Enlarged or magnified images, right? So this case has an has a specific use, and which is your makeup mirror. In makeup mirror, what happens? That a small very mirror that people carry in the vanity. So that mirror is what? Makeup mirror. So generally these mirror are meant to be used when the object is placed very close. Okay, as you watch these mirrors, you watch your reflection on these mirrors from a very close distance, that is between F and P. So what will happen? A very highly enlarged image will be formed, because that is the purpose of makeup mirror, to give you a zoomed in view of your face. So that is how this is working. Actually you are keeping the mirror very close to your face, let us say, and then you can see your face in a very enlarged image you can observe on the mirror, and that is nothing but this case, F and P. So this was all about your ray diagrams. Now let us summarize all these points that we have learned, because this is important when you are because it is important for you to remember that where the image will be formed when an object is place. So you can learn by this manner. Suppose this is the object position. This is the object position, and then we will be talking about image here. So this is image position, this is image size, and this is image nature. Okay, one by one we will discuss. So when I place the object at infinity, what I observed that the position of image was at f, and what was the size? It was highly diminished. It was highly diminished, and the nature was real and inverted because the rays were actually meeting. Second case, I took the object a bit closer to the mirror, that is beyond C. Then I observed that the image form was between F and C. Between F and C the image was formed, and now the image from highly diminished to somewhat it become increased in size, that is diminished image. Still it is diminished. Still the nature was real and inverted. Again, when I took it at C, the position of image was also at C, and now the image size was of same size. Okay, same size. Let me write it correctly. Same size of the image was observed. This time also real and inverted, that is upside down image was formed. In the fourth case, we see that when we took the object a bit more closer between C and F, now the image was formed beyond C. Okay, and now the image is getting enlarged. Still though real and inverted. Then I took it at F. Okay, at the focus point. Then the image now becomes at infinity, and it is now highly enlarged image. Still it is in the category of real and inverted because the reflected rays will be meeting somewhere at infinity and forming an image, right? And the last case is what? Between F and E. So at this point, where was the image? It was behind the mirror. Behind the mirror, and size is also enlarged. But what was the nature? Virtual and erect. Virtual and erect. Now from this you can analyze that, see the object position and see the position of this image, right? As the object position is decreasing, okay, object position is marked by U, it is marked by U. So object position, see this U is decreasing, okay, U is decreasing. What is happening? The size of the image is getting increased, okay. So you can see that object position U distance is inversely proportional to the size of image. You can see this because when it was at infinity the image size was diminished. When it was bring further closer it gets a bit enlarged, still in the category of diminished. At C it was of same size, and you further move closer the image is keeps on getting increased. So as U is getting decreased, size of image, if U getting decreased, size is getting increased in case of a concave mirror. And what about the nature? For all the case the image nature is real and inverted except for this case when the object is between F and T. Okay, so this is how you can learn. So see this, when the object is at infinity the position of image is at F, right? So when when object is at F, the image position is at infinity, it has reversed. Okay, so when object position is at C, right, object position is at C, the image formed is at between F and C, right? Now when object is between F and C, then the image position is beyond C. So this is following this kind of relation. See this. This one, let me draw this. Right. This one I am telling you that see this. Right. See this. And this. Right. So this is the case. What I am telling you, this is the case. The last case is or always is obviously a different one. But for rest, you can now it becomes easier for you to remember. When it is at infinity, the image is at f, and correspondingly, if the object is at f, the image is at infinity. That's how you can know. And the size of the image is what? Size of the image is inversely proportional to the object distance. At the object distance, you start from highly diminished, and then you keep on increasing the size as you are reducing the object distance. Okay, so this is how you can understand the image formation by concave mirrors. Now let us see one more heading, and that is nothing but the uses of concave mirrors. Uses of concave mirrors. Right. So what are the uses? First of all, I told you that makeup mirrors. Yes, it is used as makeup mirrors. Right. Why makeup mirror? Because when the object was placed between F and P, when the object was placed between F and P, an enlarged image is formed. Although it is virtual, we don't care about the nature of the image. It is virtual and erect image is formed, and that is what is required in a makeup mirror. Okay. Second is you can see it in the headlamps, okay, or the headlights of vehicle. Headlights of vehicles. Why headlight of vehicles? See this. If this was a concave mirror, when you are placing the bulb at the focus point, right? If you are placing the bulb at the focus point of the mirror, what it will be doing? The incident rays will be emitting like this, and they will become parallel to the principal axis. So you will observe this parallel beam of light. You will observe this powerful parallel beam of light. Okay, parallel beam of light, which is very great for enhanced vision, and this parallel beam of light is required. So this parallel beam of light is required, and that is why it is used in headlight of vehicles. Okay, another use of concave mirror is like the dentist's mirror. Okay, the dentists also use this mirror over their head mirrors. Okay, on the helmet, they sometimes the dentists wear a uh, mirror over their helmet or whatever. So what happens, the light in the surrounding will fall on the their concave mirror, and ultimately it will be it will be throwing a beam of light on the patient. Okay, the where they have to do the treatment. So that is how that it will be used in case of a dentist mirror also. So in whatever case a parallel beam of light is desired. Okay, also in the torches also. Okay, yeah, these torches light, this is also where the bulb is placed in the focus point, right? So this is one of the these are the some of the uses of the concave mirrors. Okay, shaving mirrors, also makeup mirrors. You can write shaving mirrors also. More or less, the concept involved is the same. So these are some of the uses of the concave mirrors. So this was all about the concave mirrors. So what in the next lecture, what we will do, we will be learning about convex mirror. Only two cases for ray diagrams are there. So we will be seeing the ray diagrams for convex mirror. We will be seeing the uses of convex mirror, and we will be learning some of the formulas which are required to determine the position of image, to determine the size of the image, to determine the nature of the image. So that formula, that is mirror formula, we will be seeing, and then we will be subsequently solving the numerical problems, different problems on this reflection topic, and that will wind up the reflection concept of light. So this is all for today's class. We will see the next mirror, that is a convex mirror, in the next class.